All right, so let's start out our journey into chemistry in Unit 1 talking about what is matter, because obviously in chemistry we're always concerned with reactions and changes in matter, and we need to understand what matter is before we can talk about those more fancy things. So first off, let's see what you know. Which of the following would you classify as matter? So your choices are light, salt, muscle, or air. So pick as many as you think classify as matter. Okay, so in order to talk about which of these things would be considered to be matter, we should take a look at the definition. So matter is anything that has mass and volume, and so we should know that mass is the measure of quantity of matter. Some units for mass would be grams, also be using metric units, so the prefix is kilogram, milligram, microgram. Those are all units of mass. And we should remember, hopefully we've seen this in another science class before, but mass is different from weight. So weight has to do with the force of gravity acting on the mass of an object. So we know like our weight on Earth would be different than our weight on the moon because there's a difference in gravity. However, mass would be something that's not going to change regardless of us being on the Earth or the moon. So even if I go to the moon, even though I might appear lighter in terms of weight, I know that I definitely am still the same old blob that I was here on Earth. So that's something important to remember. And that's why we use mass for our discussions in chemistry, because we want to be sure we're always talking about the same thing and that it's not conditional based on where we are talking about the object or the matter. Next, we've got volume, so that's the amount of space that something takes up. We will get into units in the next unit, but some volume units. We've got gallons and cups and quarts and ounces. Those are all English units. We will not be working with those in chemistry. We'll be working with liters, milliliters for the most part. There's also cubic centimeters, cubic decimeters, cubic liters. And again, we'll talk about those in the next unit. So what are the states of matter? So I think most of us at this point in our science careers have been exposed to the states of matter. So take a minute and see if you can label which picture is solid, which picture is liquid, and which is gas. Okay, so hopefully at this point you have figured out that this guy is the solid, this guy is the gas, and this guy is the liquid. And we're going to take a look at how exactly we should be identifying solids and liquids and gases. But a very, very, very important thing. So we are going to, in chemistry, be concerning ourselves with what we call the particulate view, or with the molecular view, or the atomic view. And what that means is that we're concerned with pictures like this. So what do the fundamental pieces of matter making up the substance, what do they look like? What are they doing? How are they interacting with each other? So again, this image, when we talk about the states of matter, I want these things to be what come to mind. So let's take a closer look at each one of these. So for the states of matter, first one, we can see the solid picture here. And solids have very low kinetic energy. We're going to be abbreviating kinetic energy with KE, and so you should make note of that in your notes. And kinetic energy is the energy of motion. So something that's moving has kinetic energy. And so we think of all the particles around us are always moving. The only thing that's not actually moving is if we have something that's at absolute zero, and we'll talk about that later in the year. But for solids, notice that the way these particles are drawn is that they are all touching each other. There's no space in between them, and they have a fixed pattern. So particles can vibrate. So we say they have a little bit of kinetic energy. It's very low. They can vibrate, but they can't move around. So they're locked in next to the neighbors that they're next to. So because of this, they have a fixed shape. So because those particles are not sliding past each other, moving around, their shape is unchanging. That also means they have a fixed volume. So the particles take up the space they take up. There's no empty space between them. And so they're always going to maintain a fixed volume. They're not taking up any additional space or any lesser space. Next, we've got liquid. So the liquid, notice that the particles, they're all shown down at the bottom of the container here. And they are not in that same rigid pattern that we saw with the solid. So liquids have low kinetic energy. So notice solids we described as having very low kinetic energy, and liquids have low kinetic energy. So it's still low. So it's not medium. The number one misconception that people try to write when I ask them this question. So it's still low kinetic energy, but they've got enough energy that they're able to move past each other. So later on in the year, we're going to talk about why particles stick together in the first place. There's attractions between them, and depending on what the particles are, there may be more attraction or less attraction. But they have enough energy that they're able to at least wiggle around a little bit next to their partnering atoms or molecules. So because they are able to move past each other, so they're like sliding past each other, but they are still touching, so that's very, 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 very important that we also differentiate. They're still touching. The particles are still touching each other, but they do have variable shape. So again, because the particles can sort of slip past each other, they can take on the shape of their container. And they have a fixed volume still, though. So again, if there's no space between the particles, they can't take up any more or less space than the particles themselves take up. Lastly, we've got gases, and gases have high kinetic energy, so particles can separate, so they can overcome the attractions between particles between each other and move around throughout the container, so they're not stuck to anything. They're free to roam about, and so that's why they have a variable shape, so they take on the shape of their container. So you don't want to say they have no shape, but they do take on whatever shape container they're in, because again, they'll move until they hit into the container wall. And they do have variable volume. So it's not that they have no volume. They do take up space, but it's variable. So that means, again, it's dependent on the size of the container that they're confined in, the molecules are confined in. We do also have plasma, which you may already know is the fourth state of matter. We're not really going to be dealing with that in chemistry, but we should mention it. So it has very high kinetic energy. Particles are colliding with enough energy to break into charged particles, and plasma is gas-like, so it has a variable shape and volume, so that's what I mean by it, that it's gas-like, has even more energy though, can find plasma in stars, and so that's why we're not really going to be dealing with that in here, because we're mostly talking about chemistry here on Earth. Okay, so we also know that if there's states of matter, we can change between the states of matter. And very common example we know of in its three different states of matter are water. So water is H2O, and it can be ice, which is what we call the solid. It can melt and change to liquid water, and it can also vaporize and turn into steam, which is the gas version of water. States of matter are changed as energy is added or removed. So this is something that we're going to study later on in the year. We know that also these phase transitions, so notice I'm using the word phase as another word for state of matter, but the phase transitions or state of matter transitions can happen as energy is added or removed, and you can do it reversibly one way or the other, and we'll talk about that in an upcoming presentation about how and why that's possible. But again, in order to do, like we know, in order to melt ice, there's got to be some heat being added to it. In order to freeze water, we know we've got to remove energy. We know if we want to boil water and turn it to a gas, we've got to add energy. So again, associating energy changes, state of matter changes with energy changes, that's a very important thing to keep in mind as well. And again, we will get into this idea later on in the year, but this is all, those energy changes are overcoming attractive forces between molecules, and that's what's allowing the different spacing and different orientation between the particles that we just looked at. Okay, so if we want to talk about matter, we've defined what matter is, what kind of states it can be in, but we want to describe like what makes one type of matter different from another. What characteristics are we using to tell that, hey, this is gold, this is just silver, or this is, just a big piece of rock. So pure substances, we'll define that later on, have unique chemical and physical properties that distinguish them from other substances. They don't depend on quantity. So there are what we call intensive properties and extensive properties. We're going to be talking about intensive properties. So that means it doesn't matter how much I have. If I have a cup of it, if I have a gallon of it, of a certain liquid, the characteristics that we're using to describe it don't have to do with how much of it that we have. And so again, we said those are called intensive properties. If we're talking about the size of something, the mass, the volume, the length, those would be called extensive properties. And again, those are not going to relate to the identity of the substance. I can have a pound of butter, or I can have a little pat of butter, but it's still butter. It would still have the same taste, the same color, the same characteristics. So again, extensive would be like that amount of butter measurement. Okay, so chemical properties. So these are characteristics of a substance that describe how it participates in chemical reactions. And we'll be getting into types of reactions and all that good stuff later on in the year. But some examples are actually, how do I know that something is engaging in a chemical reaction? If I'm testing its property, then we would see the composition of the substance changing. So it would not look the same before and after if we're testing a chemical property. So things like tendency to react, tendency to tarnish, which if you don't know what the word tarnish means, it means becoming dull or discolored. So like if you've ever seen a nice silver frame or silver ring or something, and it kind of gets kind of ucky and dull and discolored over time. And ucky is a technical chemistry word. That's tarnishing. So it's a reaction happening with the oxygen and air. Ability to corrode, explode, or act as a poison. So any of those things would also be describing a chemical property. Next, we've got physical property. So that's a characteristic of a substance that does not involve a chemical change to test it. So that means the composition is not affected. Some examples of those would be density. So although mass independently and volume independently are not physical properties, because I can still have the same substance and have a different mass, this ratio of mass divided by volume, that is a physical property that does not change. So, if I have a cup of water, if I have a gallon of water, the mass divided by the volume would be the same, regardless of how much I have. So density is a physical property. Color or odor, again, if something has a certain characteristic smell or has a certain characteristic color, then those would be considered physical properties. I can use it to help me pinpoint that, oh, this is a certain substance and this is not. Melting or boiling point. So the temperature where the liquid to solid phase change happens, or the liquid to gas phase change, that's the melting and boiling point. Those are physical properties. Hardness would be another example of a physical property. So again, physical properties are characteristics that can be measured and tested without changing the chemical composition. So here's some examples. We've got this nail here. And malleability is an example of a physical property, because I can test to see. So malleability we'll define later on in the year, but it's the ability to reshape something. I bent the nail, but it's still a nail made out of iron, and I did not change the fact that it's an iron nail by bending it. So that's why that's a physical property. We've got this cup containing red food coloring. So I can observe that it's red without changing the chemical composition. So that would be considered a physical property because of that. Now, looking at chemical properties, so back to the iron nail. We've all seen iron rust. I'm assuming most of us have seen iron rust or have seen something that's rusted. And that really is a reactivity with oxygen. So the fact that iron will react with oxygen, that is a chemical property. Now, what we said about determining that something's chemical or defining something as a chemical property, I couldn't tell that something will rust unless I actually try it. So once I see this iron nail rusted, then I know, hey, this iron nail has that chemical property. Looking at a chemical property for the red food coloring, we'll notice we have reactivity with bleach. So after the bleach was added, notice that we don't appear to have the red color anymore. So we no longer have the same makeup. There appears to be some sort of change that has happened to the red food coloring. Its color's gone away. So in order to test that this red food coloring has a reactivity with bleach, we actually had to cause the reaction and as a result have a change in composition. Likewise with the, going back to the nail, reactivity with oxygen. Notice I don't have the same characteristics before and after. You know when something has rusted because it turns, that characteristic reddish rust color. It has like a flakier composition. It's certainly not as hard and strong as it once was. And so, we know that it has new characteristics, new properties, that there's been a change, and that's a chemical property. So a chemical reaction must have happened because we see a change in composition once we've determined that it has that property. Okay, so we are going to practice what we just learned, identifying properties as being chemical or physical, and this is for compound X. So you're going to take a look at this list and classify each as a chemical or physical property.